The 7th of December 1941 changed everything. Within hours of the attack on Pearl Harbor, the United States Congress convened an emergency session, and Franklin Roosevelt signed a declaration of war against Japan. 3 days later, Germany and Italy reciprocated. America was now at war on two fronts, and the country's military establishment faced a statistical reality that bordered on humiliation. The United States Army Air Forces possessed approximately 55 combat-ready heavy bombers. The Luftwaffe fielded 2,500, but the numerical disadvantage was only the beginning. Buried within the crisis was a dependency nobody had thought to address. Every Wright R-1820 and Pratt & Whitney R-2800 radial engine rolling off American assembly lines relied upon a single precision component that made sustained, high-altitude flight possible: the spark plug. Not the ordinary automotive type found in a Ford sedan, but a specialized aviation spark plug capable of firing reliably through temperature cycling from minus 60 to 900 degrees Celsius, withstanding combustion pressures exceeding 1,000 pounds per square inch, and maintaining consistent ignition timing across altitude ranges where air pressure dropped to 1/4 of sea level values. These were instruments of extraordinary engineering precision, and virtually every one of them came from Germany. The Robert Bosch GmbH Corporation of Stuttgart had dominated global aviation spark plug production since the early 1920s. Their patents, their manufacturing expertise, their metallurgical knowledge accumulated across 3 decades of development. All of it belonged to the enemy. The moment war was declared, that supply chains ceased entirely. The mathematics were brutally simple. American aircraft production targets called for 47,000 engines in 1942 alone, rising to over 100,000 by 1943. Each engine required 18 spark plugs plus maintenance reserves, roughly 30 plugs per engine per year of operation. The program demanded approximately 3,000 aviation spark plugs per year. American domestic production capacity on the 7th of December, 1941, 0. Not inadequate, not insufficient. 0. Every specialized tool, every trained technician, every piece of institutional knowledge resided in Stuttgart, which was now an enemy city. Amongst the engineers and industrialists summoned to Washington in the frantic weeks that followed, one name kept appearing in the files of the War Production Board. A name that, depending on whom you asked, was either the most important in American spark plug manufacturing or the most confusing. Albert Champion was not American by birth. He was not even an engineer by training. He was born in Paris in 1878, the son of a working-class family in Montrouge, and his first career had nothing to do with internal combustion engines. Champion was a bicycle racer, and an exceptional one. By his early 20s, he had won multiple French national championships, crossed the Atlantic, and established himself as one of the finest cyclists competing on American tracks. Then, in 1904, a crash during a race in Massachusetts shattered his knee and ended his competitive career with the brutal finality that sporting injuries so often deliver. He was 26 years old. If he couldn't race, a colleague would later recall, perhaps he could improve the machines. Champion had grown up tinkering. The mechanical logic of bicycles had always interested him as much as riding them. Forced to find a new vocation, he turned his attention to the emerging automobile industry, specifically to the ignition systems that were, in the early 20th century, the most unreliable component of any motor car. Early spark plugs were ceramic insulated devices prone to cracking, fouling, and misfiring. Champion noticed what the established engineers had apparently decided to ignore, that the insulator material itself was the fundamental problem, and that improvements there would cascade through every performance characteristic. Working in a small workshop in Flint, Michigan, he developed a new approach to ceramic insulation, using a refined aluminium oxide compound that could withstand far greater thermal stress than conventional materials. The manufacturing process was painstaking. The ceramic had to be fired at precise temperatures, ground to tolerances measured in thousandths of an inch, and assembled with a consistency that early 20th century industry found genuinely difficult to achieve. Champion founded a company to commercialize his innovation in 1904, named it after himself, and began selling plugs to the nascent American automotive industry. The story of what happened next is complicated by business arrangements that would frustrate any historian. Champion, brilliant at manufacturing but less gifted in commercial negotiation, lost control of his own company in a dispute with his financial backers. The Champion Spark Plug Company continued under new ownership, whilst Albert himself was legally prohibited from using his own name for a competitor. He responded by founding AC Spark Plug, the initials standing for Albert Champion, and signing a manufacturing agreement with General Motors. For the remainder of his life, he ran AC, building it into a significant enterprise, whilst the company bearing his surname operated independently under different management. He died in Paris in 1927 and left behind 2 separate spark plug companies, both founded on his innovations, both bearing versions of his identity and neither entirely his. The legal and corporate legacy was bewildering, but the engineering legacy was not. AC Spark Plug, operating from its facility in Flint, Michigan, had by the late 1930s become a respected manufacturer of automotive ignition components. It had never, however, manufactured aviation spark plugs. That market had belonged to Bosch. When the War Production Board approached AC Spark Plug in January 1942, the company's production manager, Harold Metcalf, made a claim that many in Washington found difficult to credit. AC could retool for aviation spark plug production. AC could reach meaningful output within 6 months, and AC could ultimately supply the quantities the Air Forces required. The mathematics of what that promise entailed were staggering. AC's Flint facility was producing approximately 200 spark plugs per day for automotive applications. The Army Air Force's minimum acceptable delivery schedule required 8,000 aviation specification plugs per day by the end of June 1942, a 40-fold increase in 6 months for a product of vastly greater complexity and precision than anything the plant currently manufactured. Metcalf signed the contract on the 14th of January 1942, and the transformation began immediately. The existing production lines were partially dismantled within days. New grinding equipment arrived by rail from Cincinnati. Kilns capable of firing ceramic at 150 degrees Celsius were installed in buildings hastily constructed on the plant's east side. The workforce, which had stood at 1,400 in December 1941, grew to 3,800 by March and exceeded 9,000 by August. 67% of the new hires were women, many of them wives and daughters of men who had shipped out in the first draft calls. One of them, a 23-year-old named Dorothy Sievers from Flushing, Michigan, who had been working at a drapery shop 6 months earlier, operated a ceramic grinding station for 11 hours a day, 6 days a week. Metcalf came through once, she recalled years later, and he stopped at my machine and said, "This plug will keep a pilot alive at 30,000 feet. After that, I checked everyone twice." Production numbers followed a curve that looked on paper almost impossible. January 4th, 100 total. February, 31,000. March, 183,000. May, 387,000. June, 524,000. By August 1942, the Flint facility was producing 2,200 aviation spark plugs per day. The quality rejection rate, which had stood at 34% in February as the workforce learned the process, fell to 6% by June and to under 2% by September. The Army Air Forces did not simply accept AC's word that the plugs were adequate. In April 1942, the Air Technical Service Command administered the Standard Aviation Spark Plug Qualification Protocol, a test specifically designed to simulate the most punishing conditions any plug would face in operational service. Each candidate plug was subjected to 200 hours of continuous operation cycling between -55 and +900 degrees Celsius, firing at 1,200 volts under simulated altitude pressures, whilst subjected to vibration loads equivalent to engine operation. The established American competitors, firms that had been manufacturing spark plugs for decades, failed at an average of 67 hours. One failed at 43. The AC Aviation Plug, built on Champion's ceramic insulator principles and refined through Metcalf's production engineering, ran the full 200 hours without a single misfire. The results were not close. The Air Technical Service Command awarded contract to W535 AC 22847 on the 30th of April, 1942, 14,000 spark plugs to be delivered over 18 months at $1.47 per unit. It was, at that moment, the largest single-component contract in American aviation history. The plugs reached operational squadrons in the summer of 1942. The 97th Bombardment Group, flying B-17 Flying Fortresses from bases in England, was among the first units fully equipped with AC manufactured aviation spark plugs. Their maintenance records for the preceding period, when mixed supply had included reconditioned Bosch plugs from pre-war stocks, showed an engine abort rate of 4.3% on pre-mission run-up checks. Plugs fouling, misfiring, or failing to meet timing specifications. The records for the 3 months following full AC reequipment showed an abort rate of 0.4%. The group's engineering officer, Captain William Briggs, submitted a report to 8th Air Force Headquarters in October 1942, noting that in 847 combat sorties flown since July, there had been 0 confirmed aborts or aircraft losses attributable to spark plug failure. The ignition reliability of these units, Briggs wrote, exceeds anything previously encountered in operational service. The numbers across the wider 8th Air Force told the same story. Engine abort rates fell by 71% across all heavy bombardment groups in the 12 months, following full conversion to domestic spark plug supply. German intelligence was not unaware of what was happening across the Atlantic. A Messerschmitt Bf 110, brought down over Kent in September 1942, carried documents that included, among routine operational papers, a translated summary of captured AC spark plug samples sent to the Reichsluftfahrtministerium for analysis. The report, recovered after the war from Luftwaffe archives, acknowledged that the ceramic insulator technology in the American plugs was of a quality comparable to Bosch production standards, and that the manufacturing consistency suggests industrial capability previously underestimated. The document then noted, with the careful bureaucratic understatement of a ministry official delivering unwelcome news, that German capacity to respond in kind was constrained by current allocations of skilled labor and specialized materials. This was, by the autumn of 1942, something of an understatement. Bosch's Stuttgart facilities had been subject to RAF bombing since 1941. Skilled workers had been conscripted. Nickel alloys required for high-performance spark plug electrodes were being diverted to armor plate and aero engine production. The window within which Germany might have developed a credible alternative supply chain had, in the opinion of the Luftwaffe's own logistics officers, already closed. The strategic bombing campaign against Bosch and related facilities continued throughout 1943 and 1944, at considerable cost. The 382nd Bombardment Group lost 11 aircraft attempting to hit Stuttgart in September 1943. The Schweinfurt raids, targeting ball bearing production, cost 60 heavy bombers in a single day. Men died in quantity attempting to destroy what German industry could produce. The irony, appreciated only in retrospect, was that the effort was simultaneously heroic and redundant. Whilst American airmen were dying in attempts to prevent Germany from supplying itself with precision ignition components, the Flint facility was producing 9,200 aviation spark plugs per day. The reject rate was below 2%, and the Army Air Forces had accumulated sufficient stockpile to sustain operations for 8 months even if production had ceased entirely. The thing the bombers were trying to deny the enemy, the Americans were already producing in quantities that made denial almost irrelevant. Enemy engineering came in second place, not through defeat in laboratories or drawing offices, but through the accident of history that placed an immigrant Parisian bicycle racer in Flint, Michigan in 1904, and gave him a reason to solve a problem that would not become critical for another 37 years. Albert Champion did not live to see what his ceramic insulator technology had made possible. He died in 1927, before the air war he had unknowingly helped to win was even conceivable. The AC Spark Plug Division of General Motors continued expanding after 1945, absorbing Champion's engineering legacy into broader electronic and sensing programs. By 1960, the division employed over 22,000 workers. By 1985, Champion's ceramic insulator principles were present in every automotive oxygen sensor, every catalytic converter temperature probe, every aircraft ignition system produced in the Western world. The AC Delco brand, direct descendant of Albert Champion's Flint operation, today supplies ignition components to manufacturers across 6 continents, producing over 200,000 units annually. Every one of them carries, in its ceramic insulator, the manufacturing logic that a Parisian cyclist developed in a Michigan workshop because a crash had left him with nothing else to do. Germany, which entered the war having dominated global spark plug production for 20 years, emerged from it having lost both the market and the technological lead to a nation that, on the 7th of December 1941, had no aviation spark plug industry whatsoever. The reversal was total